the way I want to get into this is I'm gonna turn the lights off, make it easier to see the slides. But oh shoot, I think that's right. In any case, previously in this class, we did a restriction digest of a plasmid. We restriction mapped a plasmid to try and identify what plasmid was in our bacterial colonies. Was it the Piglo without Araceae that we wanted, or was it something else? And so I said at the time that that technique could be extended to genomic DNA, that you can use restriction mapping of genomic DNA to look for mutations, look for variation between different people because they will have different restriction patterns. When we did our restriction mapping of Piglo and our clone plasmid, all we did is we digested the plasmid, ran it on a gel. So the end result was electrophoresis, and you looked at the result on a gel. If you restriction map genomic DNA, you can't just run that genomic DNA on a gel. You have to do a southern blot, which looks at DNA. So I meant to animate this a little better, didn't apparently. But the reason that for genomic DNA you have to use a blot, and for plasmid DNA you only have to do electrophoresis, is because of the amount of material in genomic DNA. When you did your mini preps, basically the only thing in those mini preps was plasmid DNA. So the DNA that you wanted to look at was the only thing in your sample. If you want to use restriction mapping of genomic DNA, remember there are 2 copies of the genome per cell, and the genome is 3 billion base pairs, 3 times 10 to the 9th base pairs. And so you, at least with this kind of technique, you're never going to be able to look at the whole genome at once. You're going to want to look at a specific piece of the genome. You're going to want to look at a 2,000 base pair piece. You're going to want to look at a 10,000 base pair chunk of the genome. So if you want to look at a chunk of the genome that is twice the size of Piglo, so Piglo is about 5 kb. If you want to look at a 10 kb chunk of the genome, then you want to look at something that's 0.00033% of all the DNA in your sample. So when we did the plasmid digest, we wanted to look at something that was 100% of our sample. If we want to look at genomic DNA, we want to look at a 10 kb chunk, 10,000 base pair chunk. We want to look at something that's 0.00033% of our sample. And so this is why blotting is useful. I like to say that blotting solves the needle in a haystack problem. It allows us to look at one specific piece of DNA, one specific mRNA, one specific protein in a sample that contains thousands and thousands or millions of different DNA sequences, RNAs, or proteins. So this is why blotting is useful, because it allows us to pick out the one molecule we're interested in out of a soup of thousands or millions. So, depending on what molecule we're trying to pick out of the soup, the blot has a different name. So it is important that you guys remember this. I only really care that you remember the top 3. I'm going to mention the bottom 3, but only out of curiosity's sake. So, excuse me. What kind of blot looks at DNA? Southern blot. Exactly. So Southern blot, this was the first one invented in 1951 by a guy named E.M. Southern. So it's actually named after him. The rest of these blots are so named because scientists are not very creative. So a blot that looks at RNA, Northern blot. They stayed with the direction thing. A blot that looks at protein, Western, exactly. So now we get a little, so these are the only 3 I ask you to remember. So on your exam, on your final paper, if you're going to be looking at protein, don't start writing about a Northern blot. Write about a Western blot. if you're going to be looking at DNA, write about a southern blot. The general procedure for these blots is very similar, especially between southerns and northerns because they both look at nucleic acids. But overall, all three blots are very similar. So today what we're going to do is I'm going to talk about southerns in a lot of detail, and then talk about what's different between a northern and a southern, and then a western and a southern. And as you might imagine, westerns and southerns are more different than northerns and southerns. But blots can be extended. Rather than just looking at one type of molecule, you can kind of combine blots to look at interactions between different molecules. So what do you think a blot that looks at DNA-protein interactions is called?
Southern, western, southwestern.
Southwestern blot, exactly. Similarly, RNA-protein interactions are northwestern blots. And then there are far western blots that look at protein-protein interactions. So, so far in my career, I've seen tons of southerns, northerns, and westerns. I've done tons of northerns and westerns. I've done a couple southerns. I have seen in the literature 2 far westerns. I have never seen a northwestern or a southwestern, but they are done. But like I said, all I guys want you to remember is DNA is southern, RNA is northern, and protein is western. So the first step in performing a southern blot is to digest the DNA with restriction enzymes, usually. And so this serves 2 purposes. The first purpose for digesting your DNA sample is that basically whenever you're doing a southern, you're restriction mapping something, just like you guys already did with the plasmid DNA. And so digesting our sample with restriction enzymes allows us to look for a particular banding pattern. Just like you guys